by the end of this video, you should know the reactions of ethanol, know that carboxylic acids react just like any other acids, and understand that a reaction between an alcohol and a carboxylic acid results in the formation of a new organic molecule called an ester. In this video, I'll also be introducing the ester functional group, showing you how to form and name esters using condensation reactions, and then breaking those esters using hydrolysis reactions to form detergents. And you should also know how to distinguish between soapy and soapless detergents by the end of this video. The reactions of ethanol. So the first reaction of ethanol that we need to know is combustion. So ethanol undergoes complete combustion. That means that it burns with a clear blue flame. Just like our alkanes burn with a clear blue flame. And it's the same reason why it has a low carbon to hydrogen ratio, meaning there's no carbon left over to make soot, so there won't be any black smoky flame. And this is just a reminder of the general formula for alcohols, CnH2n plus 1 OH. So if we're doing ethanol, Eth meaning 2, that means we'll be putting in 2 carbons, and then we'll be able to figure out that ethanol will be C2H5OH. Yes? Okay. Yeah, and here's your reaction for complete combustion of ethanol. Ethanol plus oxygen will give you carbon dioxide and water vapor. Boom. The next reaction of ethanol that you need to know is that ethanol reacts with sodium to produce sodium ethoxide. Ethanol reacts with sodium to produce sodium ethoxide and hydrogen gas. So ethanol plus sodium, the sodium is going to displace the hydrogen of the ethanol. So this is going to kick out this, yes, and make sodium ethoxide. And this hydrogen that got kicked out is now going to be hydrogen gas. Make sense? So ethanol plus sodium, the sodium takes the place of the hydrogen, and we get sodium ethoxide. The name of this compound is sodium ethoxide, and you get hydrogen gas. Sodium displaces hydrogen. Makes all sense. Next reaction. The next reaction for ethanol that you need to know is dehydration of ethanol using heat and a catalyst. The catalyst in this reaction can either be concentrated sulfuric acid or aluminum oxide. When would you use which one? You use sulfuric acid if you're dehydrating a liquid sample of ethanol, and you'd use aluminum oxide if you're dehydrating a vapor sample of ethanol, a gas. And the heat, you'll heat it to 170 degrees Celsius, and the products of dehydration of ethanol will be an alkene or ethene gas and water vapor. So you're dehydrating it, so that means you're removing the water. So when you take water out of ethanol, you remain with an alkene. And because it's ethanol, the alkene will be ethene. If you dehydrate an alcohol, you'll get an alkene as the product along with the water that comes out. And you put your specifications on your arrows. So you need concentrated sulfuric acid to make this reaction happen, and you need to heat it to 170 degrees Celsius. Oxidation of ethanol is the next reaction that we need to know. So if we're oxidizing ethanol, that means that ethanol is the reducing agent because it's being oxidized. The thing that's being oxidized is the reducing agent. And whatever oxidizing agent you use would be getting reduced by the ethanol because it will be a redox reaction. Remember, reduction and oxidation normally happen together. And the products of oxidizing an alcohol or ethanol is you get a carboxylic acid and water. So if you oxidize ethanol, you get ethanoic acid and water. One way you can remember this is if you look at the general formula of alcohols and the general formula for carboxylic acids, you'll see that carboxylic acid has an added O in there because you oxidize the alcohol to make the carboxylic acid. You oxidize the alcohol to make the carboxylic acid plus water. What oxidizing agent would you use to do this? To do this reaction, you can use acidified potassium manganate 7 or acidified potassium dichromate 6. Those are two oxidizing agents that we already know about. And the one that's actually used to detect alcohol in the breathalyzer test is the acidified potassium dichromate. So acidified potassium dichromate would act as the oxidizing agent, which means itself would get reduced. What actually is happening is the dichromate is going to get reduced to chromium, and the chromate is orange and chromium is green. So if you breathe into a breathalyzer test, the acidified potassium dichromate is in there, the chromate is orange. If when you breathe into the breathalyzer, there's ethanol in your breath, the ethanol will act as a reducing agent and reduce the chromate into chromium, and it would turn green, and the police would know that you've been drinking. And as for the acidified potassium manganate, if you use this to detect it, it would go from purple and be reduced to manganese. The manganate would go from purple manganate and be reduced to manganese, which is colorless. And the final reaction of ethanols is if you react an ethanol with a carboxylic acid, you would be doing something called esterification, which basically is you would be forming an ester and water. Okay, and we'll talk more about this reaction. Since it's a reaction between ethanol and carboxylic acids, it'll also be one of the reactions for carboxylic acids, so we'll talk more about it. Before we move on to that, let's just go back through the reactions of ethanol. So, we had 5 reactions of ethanol, all of which produced water except reaction number 2, which is when ethanol reacts with sodium. Instead of producing water, it produces hydrogen gas as the other product. So in all of the other reactions of ethanol, water is the second product, except when ethanol reacts with sodium, sodium just displaces the hydrogen, and so instead of getting water, we get hydrogen gas, because only the hydrogen gets displaced. The sodium takes the place of the hydrogen to make sodium ethoxide. So we know when ethanol reacts with sodium, we get sodium ethoxide and hydrogen gas. In all other reactions of ethanol, we get water as the second product. The first reaction of ethanol was combustion. So that means you're just adding oxygen, you're burning. If you burn ethanol, it's complete combustion. So we make carbon dioxide, which would be a nice clear gas, instead of carbon monoxide, which would have black smoky flame. Yes, so this is complete combustion, so we know we make carbon dioxide, and our second product for all our ethanol reactions is water. So ethanol and oxygen, we get carbon dioxide and water vapor. Ethanol with sodium is the only one that gives us hydrogen gas, and we get sodium ethoxide when the sodium takes the place of the hydrogen. Then if we dehydrate ethanol, we have to use concentrated sulfuric acid and 170 degrees Celsius, and we dehydrate it, we get the water, and our other product is an alkene, in this case ethene, because it's ethanol, they match. Oxidation of ethanol, that's when we're using an oxidizing agent like acidified potassium dichromate in the breathalyzer test that goes from orange to green, and we get a carboxylic acid and water. So we get the other functional group, the other homologous series that we know, ethanoic acid and water, when we do oxidation. Right? And then the last one was esterification, which also made water and a new functional group, which is an ester. This is when we combine ethanol and carboxylic acids. Okay, so now we're going to do reactions of carboxylic acids. And carboxylic acids are just weak acids. Carboxylic acids react just like all other acids. When they react with metals, bases, metal carbonates, they react and they produce salts. So remember, acids produce salts. And they produce salts by displacement, just similar to what we just saw with the ethanol. Basically, the hydrogens in the acid get displaced by a metal, and that new compound that's formed between the metal and what's left of the acid after you remove their hydrogens is a salt. So the salt of ethanoic acids is ethanoates. So when these carboxylic acids, when a carboxylic acid reacts, it's going to make an ethanoate, a salt, because it's an acid and it's going to make a salt. The salt of ethanoic acid is ethanoates. When acids react with metals, you produce a salt and hydrogen gas, because the metal is just taking the place of the hydrogen, kicking out the hydrogen, and so you get the metal and hydrogen gas. So when acids react with metals, you get a salt and hydrogen gas. So when ethanoic acid reacts with a metal like magnesium, you would get magnesium ethanoate, that's your salt, and hydrogen gas. The metal displaces or replaces the hydrogen from the functional group. This is why carboxylic acid is called a weak acid, because when it ionizes, when it turns into its ions, it only loses this hydrogen at the end. It doesn't lose all of its hydrogens. Strong acids would lose all of their hydrogens. They would fully ionize, but weak acids only partially ionize. So when ethanoic acid ionizes, it only loses its hydrogen. This hydrogen, not all the hydrogens. Okay, the next reaction is when an acid reacts with the base. And we all know this reaction. It's one of everyone's favorite reactions, neutralization. When you react an acid with a base, you do a neutralization reaction, because the acid gets neutralized and the base also gets neutralized. They get neutralized into a salt and our most famous neutral substance, water. Yes, so an acid and a base, you're going to get a salt and water. Your acid in this case is ethanoic acid. So that's the acid that's giving up the hydrogen. And then your bases have to give you the oxygen part of the water, because you have hydrogen and oxygen. Your bases are metal oxides and metal hydroxides. So if you have magnesium oxide, magnesium hydroxide, sodium oxide, sodium hydroxide, any metal name that you put in front of oxide and hydroxide, that new compound is a base. So you have your ethanoic acid and a metal oxide or metal hydroxide, that's the base. You're doing a neutralization reaction. You're making your salt, your ethanoate, whatever metal it is, ethanoate, and water, because it's a neutralization. Your next reaction of carboxylic acids is going to be when an acid reacts with a metal carbonate, you make a salt, carbon dioxide gas, and water. The next reaction of carboxylic acids is just going to be when an acid reacts with a metal carbonate, it will make a salt, carbon dioxide gas, and water. This is the only reaction that has 3 products. Is when an acid reacts with a metal carbonate. Then you'll get the salt, carbon dioxide, and water. So when ethanoic acid reacts with calcium carbonate, or you can use any metal carbonate, sodium carbonate, just put a metal in front of carbonate. Once the acid is reacting with the metal carbonate, what's going to happen is the metal is going to take the place of the hydrogen and make the salt. So we have calcium ethanoate, 2 hydrogens along with 1 oxygen from here is going to make the water, and what's left would be CO2, which is carbon dioxide gas. And the final reaction for carboxylic acids is esterification, which brings us full circle to our reactions of alcohols and our reactions of carboxylic acids. When you mix the carboxylic acid with the alcohol, you get a new organic molecule, which is the ester, and water. If you add an alcohol and an acid together, what happens is the alcohol gives up its entire OH. The acid continues to act like an acid and gives up an H, because that's what acids do. They donate protons, hydrogens. So this OH and this H together, that's where we get this water molecule from. And so it's called a condensation reaction. These two condense to make water, condensation. Also notice that you have special conditions for esterification, which is a catalyst of concentrated sulfuric acid and heat. And these are the same conditions that were needed to dehydrate ethanol, to dehydrate an alcohol. So it's not like you're memorizing new conditions. Same conditions for esterification as dehydration. So let's just recap really quickly our reactions for carboxylic acids. So if our reactions for carboxylic acids, you did the reaction of an acid with a metal, acid with a base, and acid with a metal carbonate. Acid with metal, we know that it's just the metal displaces the hydrogen, you get a salt and hydrogen gas. The next reaction was acid with the base, which we know is a neutralization reaction, so you're getting a salt and water this time. And then when we react an acid with a metal carbonate, that's when you get 3 products, which would be a salt, carbon dioxide, and water. And our final reaction is esterification, where we make an ester from carboxylic acid and alcohol with a concentrated sulfuric acid, catalyst, and heat. In this case, the ester is called propyl ethanoate. So it's ethanoic acid. So you see the salt part of the name comes from the acid and the beginning of the name comes from the alcohol. So if it's propanol, it'll be propyl ethanoate and water. And it's a condensation reaction because the H from the acid and the OH from the alcohol condense to give you water. Okay, so let's take a closer look at esterification. So when we mix ethanol and a carboxylic acid, so let's say we mix ethanol and ethanoic acid, you're going to get an ester called ethyl ethanoate. Now, for this reaction to happen, to do this reaction, you need to have a catalyst, which is concentrated sulfuric acid, and you need to also add heat. Now, let's look at how we get the ester and water. So, to get the ester, ethanol and ethanoic acid have to combine. The acid will be giving up a hydrogen, as all acids do, and the alcohol will give up its entire hydroxyl group, the OH. Together, this will make water. Over here, we see the water that's formed from this. This is condensation because 2 molecules react by losing a water molecule from between them. So it's a condensation reaction. And then these 2 are going to combine together. These 2 are also going to condense into 1 molecule. And you see what will be in between them is just an O. So it will be the alcohol propyl group, the alcohol's alkyl group, and an O in between them, and then the carboxylic acid side. And that's how an ester looks. So in between an ester, you'll see a lone O in between carbons. That's an ester. So now let's formally introduce esters, the new homologous series. So if you want to add it to the table from the first video, you'll have esters. Their functional group is going to be written as COO, or C and then a double bond O to another O. And when you're naming them, you're going to have whatever prefix the alcohol has plus -yle at the front, and whatever prefix the carboxylic acid has plus anoate. Yes? So if you have, let's say, let's use this same example. So if you had methanol as your alcohol, then the first part of the name would be methyl. And then if you had the carboxylic acid was ethanoic acid, then the second part of the name would be ethanoate. So whatever the alcohol, -yle, carboxylic acid, anoate. The general formula is CnH2n plus 1, and then your functional group, COO, and then CXH2x plus 1. So this is going to be your first general formula where you have N's and X's. That's because the N's are for the carboxylic acid piece, whatever prefix carboxylic acid, and the X is for the alcohol piece, whatever prefix alcohol. And here's our structural formula. So if it's methyl ethanoate, then normally we're going to put the carboxylic acid side first. So this is the carboxylic acid side because we can see the C double bond O on over here. So we know that's Eth, so that should be 2 C's in that side. And on this side, you have the alcohol side, and it's meth, so it's only 1 C. That's that. And then condensed formula, you're right, using your general formula. So you have CH3, because that's on the carboxyl side. So this CH, so a C with 3 H's, and then your COO in the middle. That's your functional group in the middle, and then CH3 at the end. So yeah, special fun facts about esters. So esters, the compounds that are formed when carboxylic acids and alcohols react, they tend to have very distinct, sweet, fruity smells. So they're going to be used to make your perfumes, food flavorings, essence, and soaps. Things that have nice smells, think esters. So if they give you a question that's asking you about something that they're specifically stressing the scent, and the scent is a sweet scent, it's most likely an ester. So if you had to name the ester formed when we have propanoic acid and methanol, remember the acid is the anoate part, is the end of the word. So this is going to be propanoate, and the alcohol is the beginning of the word. So this is going to be methyl. So this would make methyl propanoate. Yes. And this one, the acid would be methanoate, and the alcohol would be butyl. So butyl methanoate. This one, you would have butanoate and ethyl. So we have ethyl butanoate. And let's actually draw one of these. So let's do propanoic acid and methanol. So propanoic acid, so that means it has 3 carbons. Prop is for 3, and let's just get this out of the way now. So meth is 1 carbon. So prop, we have 3 carbons, and it's an acid, so I know it's double bond O, OH. Then I fill my rest carbons, making sure they have only 4 bonds around them with hydrogens. So that's propanoic acid, and plus methanol. So meth means 1, and then it's an alcohol, so that means it has an OH group. And then I fill my carbons with 4 bonds around them, hydrogens. So that's propanoic acid and methanol. And what's going to happen is they're going to condense. The acid only giving 1 hydrogen. They're going to condense and form. There's going to be 3 C's there and connected to an O in between, and only 1 C over here. This one is filled with H's, that's easy. This C has the double bond O, and all the rest are H's. And this is our ester right here. What's going to be the name of it? We already know it's the alcohol, so methyl. And the side with the acid has 3, so propanoate. And we know this formed a water molecule here. And that's esterification. Now, it's important to note that esterification is a reversible reaction. So when you're going forward, when you're doing a carboxylic acid plus an alcohol, you make an ester and water. That's your condensation reaction, because you remove the water and join 2 molecules together to form the ester. But the backwards reaction of that would be, if you looked at it backwards, you would be adding a water to an ester, and it would cause the ester to split back into carboxylic acid and an alcohol. That's the reverse reaction. The backward reaction would be adding water to the ester, causes it to split back into carboxylic acid and the alcohol. This is called a hydrolysis reaction, because hydro is water, because we're adding water. Lysis means to split into 2 or break, so you use water to break the ester. That's hydrolysis. So the forward reaction to make an ester is esterification, and the backward reaction to break an ester is hydrolysis. So you add water and you break the ester back into carboxylic acid and alcohol. For esters, this water, to break it, this water can come from either dilute acids or aqueous alkalis. So dilute tells you there's a lot of water. So this water can either come from dilute acids or aqueous alkalis. So if you use a dilute acid to split the ester, then it would be called acid hydrolysis of the ester. If you use an aqueous alkali, you'll be doing alkaline hydrolysis of the ester. Another name for alkaline hydrolysis could be saponification. And you will see why very soon. Hint, it has to do with soap. So saponification would be alkaline hydrolysis. Acid hydrolysis would just be acid hydrolysis. In acid hydrolysis of the ester, so that means you're doing hydrolysis, you're adding water, and this time you're going to be using, for it to be acid hydrolysis, you're going to use dilute acid as the catalyst. So use dilute acid and heat, and what you're doing when you do acid hydrolysis is just splitting the ester back into the carboxylic acid and the alcohol. So if it's butyl ethanoate, when it splits, remember the ethanoate part is the acid part, so it was split into ethanoic acid, and this is the alcohol part and butanol. In alkaline hydrolysis of the ester is going to be heated with sodium or potassium hydroxide solution. So your alkali is going to be either sodium hydroxide or potassium hydroxide. And what's going to happen is, since it's alkaline hydrolysis, instead of producing a carboxylic acid and an alcohol, it would produce a salt of a carboxylic acid and an alcohol, because this is not going to produce an acid because it's not acid hydrolysis. So alkaline hydrolysis of an ester, still using water to split the ester, but because it's being done with an alkaline catalyst, the product is going to be sodium ethanoate from the ethanoic acid. Instead of making ethanoic acid, it would make sodium ethanoate, and the alcohol still gets to separate, so the alcohol methyl would become methanol. If you do alkaline hydrolysis on large esters, like the esters in animal fats and vegetable oils, then you'll produce sodium or potassium salts of long-chain carboxylic acids, and those will be called fatty acids or soap. And the alcohol that you'll produce is glycerol. So that would be saponification. So saponification is when you do alkaline hydrolysis of large esters, like the esters found in animal fats and vegetable oils. When you do alkaline hydrolysis on animal fats and vegetable oils, you make fatty acids. So that sodium salt or potassium salt is going to be called a fatty acid, and that's what we call soap. That's soap that we know. We're still going to produce an alcohol. That alcohol is going to be glycerol when you do those long esters. And that's called saponification because you're making soap. So, just one more time, just to be clear, saponification is making soap from the alkaline hydrolysis of large esters found in animal fats and vegetable oils. So this is the reaction for saponification. You have a fat or oil, and you're using sodium hydroxide because it's alkaline hydrolysis, and heat, and we make soap and glycerol. That's the alcohol. Now, why is it important to make detergents? What is a detergent? Detergent is a chemical that we add to water to help remove dirt from things. Okay, now detergents are made of long molecules that have a hydrophilic or ionic head. That means the head of the molecule loves water, it's hydrophilic, it likes water, and it has a hydrophobic tail. So the tails, they're hydrophobic, that means they're afraid of water, they're water-faring, or they don't like water. And that makes up a detergent molecule. So detergent, they have a side that likes water, and they also have a side that does not like water. And that's what makes them be able to do their work. Oily or greasy dirt is often hydrophobic because we know oil does not mix with water. So oily or greasy dirt is hydrophobic. They don't like water. So if you try to wash something that was greasy or oily, like if you just ate KFC and then you drank from your water bottle, and then you try to wash the grease off the water bottle with water, what happens is the dirt clings to the surface instead of washing off. Instead of washing off or washing away with the water, the dirt will cling to the surface. So you'll see here that I have my little dirt molecules on the water bottle. You're trying to rinse it off with water, but the dirt is clinging to the water bottle because it doesn't like water. It doesn't want to wash away with the water. And so your water bottle is still greasy. Detergent molecules, or in this case soap, the soap that you would add, the detergent molecules, they can arrange themselves into micelles, which are these like balls. So they can arrange themselves into micelles to travel in water by placing their hydrophobic tails all inwards and their hydrophilic heads outwards. So they make basically a ball where on the outside they face the side of themselves that like water, so they can travel in the water, and the hydrophobic part is inside the ball, so the hydrophobic part doesn't ever actually have to contact the water. So they make these missiles, and you have the hydrophilic heads on the outside and the hydrophobic tails on the inside. Why is that important? What does that do for us? When we add the detergent molecules now, the soap, into the water, they can act like a SWAT team. They huddle together, they make their formation, they can travel through the water, go to the surface of the bottle, and that dirt molecule that was clinging on before will now feel okay in the middle here, because in the middle here is hydrophobic. There's no water inside of the detergent molecules. So the dirt will come off and go inside the detergent molecules, and then they can get washed away with the water. So when you add the detergent molecules into the water, they act like a SWAT team, forming a missile that traps the hydrophobic dirt in the center so it can be washed away by the water. The final thing you need to know for this video is soapy and soapless detergents. So soapy detergents, soap is made from saponification of animal fats or vegetable oils, whereas soapless detergents are made from petroleum. So we already see that our soapy detergents are made from renewable resources, whereas our soapless detergents are made from petroleum, which is a non-renewable resource. That means we can use this up. We can run out, but we can't run out of soap. We can run out of soapless detergents. Now, what's the difference? Soapy detergents only get soapy, even though they're called soapy detergents, they only get soapy in soft water. In hard water, that's water that has in calcium or magnesium, they do not lather. You don't see the bubbles, because instead of seeing bubbles, you'll see scum. You see like a solid, pasty solid that keeps coming out instead of bubbles. That's because it's hard water, and instead of making sodium or potassium salt, which would be your ester, it's making calcium and magnesium salts that are insoluble. That's the scum. So the calcium and magnesium that's dissolved in the water, making the water hard, are going to start coming out as a precipitate. So the calcium or the magnesium in the hard water that's making the water hard is going to start coming out as a precipitate, making scum when you try to add soap to it, until all the calcium and magnesium comes out of the water. Whereas soapless detergents will get soapy no matter what. They get soapy in hard water, they get soapy in soft water. The calcium and magnesium salts of soapless detergents are soluble, and so there's no scum with soapless detergents. Now, on the one hand, you start to think that then why wouldn't we want the one that lathers all the time and does not make scum? But the answer is no, because if you have something that lathers all the time, even in hard water, that means the hard water that's in our sewage and the hard water that's in your waterways, like some of your ponds and lakes, it means that it will still be getting soapy. The soapless detergents are still lathering, even when it's in sewage and when it's in your waterways, which means that it's going to have foam all over the top of the sewage, foam all over the tops of the ponds and the lakes, and that's going to prevent oxygen from dissolving into the waters, and so all the aquatic life would die. Whereas in soapy detergents, they'll get soapy in soft water, which we're using in our homes to wash our clothes and wash our dishes. But when it gets into hard water like sewage and your ponds and your lakes, it won't get soapy, and so the oxygen can still dissolve into the waters and the aquatic life can still live. So we see that's why it's good that soapy detergents do not lather in hard water. We also see that soapy detergents are biodegradable, whereas soapless detergents are non-biodegradable. And soapy detergents do not have in phosphates, so there's no pollution caused. Whereas soapless detergents have in phosphates, and phosphates will cause the algae to grow. So a bunch of algae, green algae, is going to grow on the ponds and the lakes and cover them, and eventually the algae will use up all the oxygen, and oxygen won't be getting to dissolving. The aquatic life will die, will create these dead zones. Yeah, it's called eutrophication. So overall, we see that soapy detergents are better for the environment.